Welcome to part 2 of simultaneous games. In this lesson, I'm going to talk about the Nash equilibrium. A solution via iterated elimination of pure dominated strategies is not always possible, and I'll show you that in this example. First, I'll introduce the example, then on the next slide, we'll introduce it. So we have players 1 and 2. Let me point to the bullets here. Players 1 and 2, both AI applications, can decide to cooperate on a complex task A with respective payoffs 7 and 5, this cell here. Players 1 and 2 can decide to independently work on different instances of a less complex task B with payoffs 3 and 2. If one player works on task A and the other on B, the player working on task A will get a score of -10. It's the -10 here and here. Since task A requires both applications, in this case player 1 and 2, they're the applications. However, the player working on B does have a positive payoff, 4 for player 1 or 3 for player 2. That's this here. Okay, on the next slide we'll analyze this situation, and we'll see that a solution is not possible in this case. I copied our game from the previous slide here, and the first point is player 1 cannot determine whether it is better to play A or B independent of what player 2 decides. You can see that here. Player 1 has a better strategy A if player 2 plays A, because 7 is better than 4. But if player 2 played B, then player A would be better off playing B since 3 is greater than -10. And you have the same problem with player 2. It doesn't have a dominant strategy in every case. It needs to know what the other player is doing in order to pick its best solution. So there are no dominated strategies in this game. However, there are still two no regret solutions, 7-5 and 3-2, these two here. And just to remind you, we did talk about this on the last lesson, but I'll repeat the definition here. A strategy profile is no regret solution if no player can obtain a higher payoff by changing only their strategy while the other player's strategies held fixed. So you can see here, 7-5 is a no regret strategy, because if player 1 switched from A to B, then it would lose 3. And if player 2 switched from A to B, it would lose 2. So this is a no regret strategy. You have the same thing down here. From 3-2, if A went to player 1 went to A, then it would go to -10, so it would lose there. And if player 2 went from B to A, it would lose 12. Right? It would go from 2 to -10. So some additional terminology. The strategy profile AA is said to be payoff dominant since it provides higher payoffs for all players than all other no regret solutions. So 7-5 is better than 3-2. And however, strategy profile BB is said to be risk dominant since the loss from deviating from BB is greater than from deviating from AA. So we can look at that here in these two bullets. If player 1 deviates from BB by playing A, it loses 13 points, right? It goes from 3 to -10. And if player 2 deviates from BB, it loses 12 points, going from 2 to -10. On the other hand, if player 1 deviates from AA by playing B, it goes from 7 to 4, so it only loses 3 points there. And if player 2 deviates from AA by playing B, it loses 2 points. It goes from 5 to 3, so it loses 2 points. So for this game, AA is the better target if each player is confident the other will cooperate. But BB is the safer choice without that confidence, right? Because you have less to lose if you guessed wrong in that case. Okay, so we have some additional terminology and a repeat of definition that we had from the previous lesson. On this slide, I have a variation of the game from the previous slide. I've changed this cell to 8-6. The other cells are the same. In this variation, there are two no-regret solutions as before, AA and BB. However, the profile BB is a no-regret solution that is both payoff-dominant. You can see that 8-6 is better than 7-5, but it's also risk-dominant. And we can see that by looking at the switching off from 8-6. If player 1 goes from B to A, it's a loss of 18. And if player 2 goes from B to A, it's a loss of 16. However, if you switch off of 7-5, for player 1 it would be a loss of 3, and for player 2 it would be a loss of 2. So I just wanted to show that it was possible to have both payoff dominant and risk dominant in the same no regret solution, which we have here. So they don't need to fall on different no regret solutions when you have more than one. On this slide, I have two definitions of the Nash equilibrium. It's named after the mathematician John Nash. And we've seen this equilibrium already. We just haven't given a name to it yet. The two definitions are the same. One is just verbal, which is this top paragraph, and the other one is more mathematical. Let's look at the verbal description first. So in general, if each player in a game has chosen a strategy and no player can increase their own expected payoff by changing their strategy while the other players keep theirs unchanged, then the current set of strategy choices constitutes what is called a Nash equilibrium. There are no regrets when a Nash equilibrium is played. A successfully iterated elimination of strictly dominated pure strategies results in a Nash equilibrium. But as we've seen in the above examples, it is possible to have Nash equilibriums even when iterated elimination of strictly dominated pure strategies does not apply. Then here is the more, I guess, mathematical or notation-based definition. So a strategy profile, so I'm just writing this in terms of notation, is a Nash equilibrium. So there's n players, I should say here. If and only if S sub I star is the best response given the other players' choices. That's why the S sub I star is not in the list here. And I guess you could actually say there's a third definition here based on the expected payoff. So the expected payoff for each player I is greater than or equal to the expected payoff if they change their selection, player I changed their selection to any other strategy. This selection is greater than or equal to. Okay, so we've seen this before. This is sort of the technical definition, and we'll use this in a proof. Actually, we'll use this third definition in a proof on the next slide. On this slide, I have a proof that the dominant strategy equilibrium implies a Nash equilibrium. That's what's stated here. And I copied the definition of dominant strategy equilibrium from the previous lesson down here, in case you've forgotten it. And then I also copied the definition of Nash equilibrium. That was the third one we had at the bottom of the last slide. So we need to show this implies this. So we are given S star is a dominant strategy equilibrium. take any player I. By the definition, S sub I star is weakly dominant strategy for player I, which means this here. So for any given S sub I, we have the taking the S sub I star from this dominant strategy is greater than or equal to the payoff for the when you're just using any other S sub I in here. This, and recall this S sub not I is just the other, any, in this case, any other selection of strategies for the n minus 1 players, what players other than I. And this holds for any such S sub not I. So we can take a particular one from this list here and just plug that into this inequality, and we get this. And since I and S sub I were chosen arbitrarily in the above argument, S star is a Nash equilibrium. And notice this here is exactly the third definition we gave for Nash equilibrium. Okay, so the main thing to remember here is dominant strategy equilibrium implies that it's also a Nash equilibrium. It doesn't work in the other direction. I talk about that on the next slide. The converse of the above theorem from the previous slide is not in general true. In the game displayed below, we have two Nash let me point to it. We have two Nash equilibria, AX and BY. They're both no regret solutions, but neither strategy, A nor B, or X nor Y for player 2, are dominant strategies. So further, there can be at most one strictly dominant strategy equilibrium. There could be more than one weakly dominant strategy equilibrium. We saw an example of that. But as our examples demonstrate, there can be several Nash equilibria for a game. We have the following algorithm for finding Nash equilibria. First step is for player 1. I mean, you could start with any player, but just to be definite here. For player 1, determine the best response for each combination of the other player's strategies. Put a mark against each best strategy for player 1. Do the same for players 2, 3, up to n. Each combination of strategies where each constituent strategy is the best strategy for all players is a Nash equilibrium. So let's look at an example of that. This seems a bit abstract here, but I have an example for you. So let's illustrate the algorithm in this example here. We have a game where each player simultaneously chooses an integer from 0 to 3. Both players initially receive a base payoff equal to the smaller of the two chosen integers. If the choices are unequal, the player who chose the larger integer transfers 2 payoff points to the player who chose the smaller integer. Thus, 2 points are subtracted from the larger chooser's payoff and added to the smaller chooser's payoff. If the players choose the same integer, no transfer occurs. So we can see that here. If they both choose 0 or 1 or 2, they just get what they've selected. So that's their payoff. If player 1 chooses 1, which is bigger than 0, then it has to give 2 points. Well, first of all, they both get the smaller of the two. So they would both get 0 as the base payoff, smaller of the two. And then since player 1 in all three of these cases chose a larger number, it needs to give 2 points to player 2. That's why you have a -2 here. And then, of course, player 2 has a +2. Let's look at just maybe one more. So player two chooses 1 and player 1 chooses 0, then you have just the opposite of what we explained here. Since player 2 chose the larger number and the base payoff is 0, smaller of the 1 and 0, you have to subtract 2 from player 1 and give that to, subtract 2 from player 2 and give that to player 1. And we looked at this case already. And then for these two cases here, the smaller number is 1. So the base is 1, but then player 1 has chosen a larger number, so you subtract 2 from player 1 to get a -1 here, and then you add that to the 1 that's given to player 2. Okay, so that's what this is. It's symmetric. You can see how these flip on either side here. For example, 4-0 and 0-4. So getting back to the algorithm, we first determine player's 1 best response for each possible choice of player 2. So maybe I should draw on the slide. So if player 2 chooses 0, the best response from player 1 is 0, right? This here, put a mark there. Since all the other ones are -2, if player 2 chooses 1, then player 1 would do best by picking 0. That would be because you get 2 in there. And then let's see, in this case, player 1 wants to get a 3, so we would choose 1. And the last one would be 4, so player 1 would choose 2. Okay, so we put a mark next to these. Now we need to continue on the next slide. Let's do that. Let's continue with the problem. I carried over our matrix from the previous slide. You notice I put in stars here where I had red check marks. Now we need to do the same thing for player 2. So if player 1 chooses 0, player 2's best choice would be this, to choose 0 also, because it gets 0 as opposed to -2, -2, -2. If player 1 chose 1, the best solution for player 2 was 2. If player 1 chose 2, the best choice is for player 2 to choose 1. It gets a 3 in that case. Again, we're looking at the second component. And if player 1 chose 3, the best choice for player 2, the highest payout, would be here. So it would choose 2 and get a 4. Okay, then the final step is we search through all our check marks and we see which, if any of them have 2 stars, and this is the only one. So the only Nash equilibrium for this game is 0-0, and this is the only no regret solution. Other solutions, in other words, other combinations of strategies from the 2 players, are higher for both players, but for example, 3-3, both players would do better than 0-0, but they're not stable. So for example, if player 1 is told player 2 is going to choose 3, so in other words, this column here, player 1 is just going to go to choose 2 because player 1 can get a 4 there, and then player 2 loses out getting a 0. So that's why it's not a stable solution. You may want to check 2, 2, and 1, 1, but none of these are stable solutions. Okay, so that's the only Nash equilibrium for this particular problem, 0-0. I have an exercise you may want to try. It's the table shown here. There's 2 players, 3 strategies for each, and these are the payoffs. And the problem is to find the Nash equilibria for this game. I'll show you the solution on this slide. So if you want to give it a try, pause the video here. Okay, I'm back. Here's the solution. For two-player games, there's a simpler algorithm to find Nash equilibria. For each strategy combination, check to see if player one's outcome is greater than its other outcomes in the same row, and check to see if player two's outcome is greater than its other outcomes in the same column. So if we look at this one here, 2347, we see that 23 is bigger than -3 and 4. And we also see 47 is bigger than 2 and 7. So given this algorithm that we've just described, this 2347 would be a Nash equilibrium for this game. I'll leave it for you to check, but the 1319 and 3137 are also Nash equilibria for this game. So we have 3 in this case. Not all games have a Nash equilibrium consisting of pure strategies. For example, neither the pitching pennies game nor the rock, scissors, paper game have pure strategies Nash equilibria. And I can show that in the table here. I went through the algorithm for both of these, and I put the little stars next to the appropriate item. We can maybe just look at this first one here. So for player A, if player B plays heads, then the better is 3. So A would want to have heads in that case. So we put a star next to 3. Then if player B plays tails, I realize he's not playing tails or she's not playing tails. It's a random toss. But in the case of tails, A does better with tails also, because A wins when the two pennies match. And then you can do the same thing for B. When A plays heads, the better choice is tails. And when A plays tails, the better choice is heads. So no one cell has a star next to each component. And that means there's no Nash equilibrium in this problem. You can do the same analysis for the rock, scissors, paper. And again, you see that there's no cell that has 2 stars. And so there's no equilibrium in that case either. The way we handle this is we have probabilities. Each strategy is played a percentage of the time, and that'll give us effectively an equilibrium solution. That takes a little bit of development to explain that, and we'll do that in the next lesson. So stay tuned for the next lesson. If you like this lesson, please give it a thumbs up, and see you soon in the next lesson.